taking the last column. All right. Okay, so that's my A right-hand side. Then I construct my original right-hand side B, and instead of A backslash B, I have A backslash minus whatever my right boundary condition is times A right-hand side, right? So that's corresponding to the new formula I have here. So let's actually set a boundary condition. For example, let's set something, let's say, how about -1? All right. And let's see how it goes. So, and after I solve for the u's, remember, I still need to enforce my boundary condition. So let me put A here. My left boundary condition is 0, right boundary condition is A, and let's plot it. All right. My analytical solution is going to be wrong, but let's run it anyway to see what we get. It doesn't look like it's correct, but I think I might have a sign error somewhere. Let me see. Do I have a sign error? Oh, yes, I have a sign error here. So I put a -1 here, but like I forget to put my minus here. So let's run it again. Close, and let's run it again. Okay, now we seems to get a reasonable answer. So the red line is my former analytical solution. I have to modify it, but the blue line is the new solution I get, and it does satisfy the boundary condition of u1 equal to my -1, right? And I think I need to figure out what the analytical solution is. I think I can just subtract the u exact with a linear solution, right? With a linear function. If I subtract x fine, I think, or actually plus a times x fine. I think that's probably a more general answer. So let me close, run it. Yes. So now I have an numerical solution, blue, and the analytical solution, red. All right. Okay, any questions on this? So we are able to successfully enforce a boundary condition on the right. Right. Okay, so let's also try something on the left, right? And actually, you can go through the derivation, but something on the left is actually also pretty easy. And I only need to put in the second row and the first, second row, first column is equal to -1 divided by x2 minus x1. Okay, so that's going to be the additional entry we need on the left. So let me call this a right-hand side at 1. Let me call this at 0 is going to be 2 to the n 1. Okay, so let's also call the right-hand side. So sorry, a1 and our a0. So let's also make it -1 to see how do we do that. And we have a1 times a right-hand side 1, and we also have another term that is a0 times a right-hand side 0. Okay, and here when we have our analytical solution, we need to our boundary condition a0 and a1. Our analytical solution, I think we need to have a 0 on the left-hand side and plus a 1 minus a 0, right? That's going to be my linear function to add to the analytical solution. So running this, we get now satisfying both boundary conditions on the left and on the right, and matches our analytical solution pretty well. All right. So now we have discussed how to enforce actually one kind of boundary condition for finite elements. That is what we call Dirichlet boundary condition. That kind of boundary condition basically specifies what the values of the solution is at the boundary. Now you may ask, what other kind of boundary condition I may have, right? And it turns out that I could actually have quite a lot variety of other type of boundary conditions. And this kind of boundary condition actually corresponds to one particular type of physical boundary condition I may have. That is, let's actually turn on a little bit to discuss what is actually physically I'm specifying here. Okay,